last problem we have to get to, since I got cut off in the last video, is problem number 60 from chapter 22, which says you have one horizontal wire with a current going to the right, and the current has a value of 14 amps. And under that, you have a loop of wire that has current going clockwise, and that loop has a current of 2.5 amps. And they give you some distances. The length of the side of the loop is 1 meter, 'cause it's a square loop. And then the distance between the top part of the loop and the individual wire is 0.2 meters, making the distance between the top wire and the bottom part of the loop 1.2 meters. Now, the first thing you have to think about in A is just what's going to happen, which way is the loop going to be forced. Now, if you first ignore the bottom part of the loop here and you just consider these two wires, notice the current is going in the same direction, and so these two wires would actually be attracted, and this wire, therefore, from the loop would feel a force upward. Now, due to the bottom one here, if you ignore the top loop right there, and you're looking at the sole wire here and the bottom part of the loop, the currents are going the opposite direction, so the bottom loop is going to feel a force downward. Now, this force downward is actually going to be smaller than this force upward, because this wire up here is in a stronger part of the magnetic field due to this sole wire, and so therefore it's going to experience a stronger force. Now, the two vertical sides here are going to have zero force, because their current is actually perpendicular to the way that the induced magnetic field would be created there. So in this part A here, overall the loop would want to move upward, again because this part of the loop is closer to the sole wire and the currents are going in the same direction. So now we actually want to figure out what is that net force. Part B is asking us to actually find what that net force is. So first thing, our equation for the force on either of these loops is going to be F equals Bill sine theta. And let's think about how this can simplify a little bit. Well, B is the magnetic field created by that top horizontal wire, and so it's going to have a value of mu times I, which I'll call I1, divided by 2 pi times R, where R is however far away you are from that wire. And then this next I that's the current that you're putting in the magnetic field, so I'll call that I2. L is the length of the wire that's in the magnetic field. And then finally, in this case, the sine of theta is going to drop because the magnetic field is perpendicular to the current. So first, if I want to find the force on the top part of the loop, what I'm going to get is mu, so 4 pi times 10 to the negative 7th, times I1, which is 14 amps, that's what's setting up the magnetic field, divided by 2 pi times the distance away, which is 0.2 from the lone wire to the top part of the loop, and then multiply that by I2, which is 2.5 amps, that's how much current's going through the top part of the loop, times the length, or the side of the square, which is 1 meter. And if you multiply all that out, what you go ahead and get is your total force is 3.5 times 10 to the negative 5th Teslas, and I'm going to say that direction is up. And now we can go ahead and do the exact same thing for the force on the bottom part of the loop. And so we would get 4 pi times 10 to the negative 7th times 14 divided by 2 pi. And this is the only part that changes here. Now the bottom part of the loop is not just 0.2 meters away from that 14 amp wire, it is 1.2 meters away. So that 1.2 goes there. The current is still 2.5 amps in the bottom part of the wire, and the wire still has a length of 1 meter. So if you multiply that, you get a total of 5.83 times 10 to the negative 6 Teslas, and that force would be down. And now it's just a situation of finding your net force. And so the sum of your forces is the top one is going to move it up, so I'll call that a positive 3.5 times 10 to the negative fifth Teslas. And the bottom one that we just solved for, that force is going to be moving it down, and I just realized I called the unit of force Teslas, which is wrong. They should be newtons and newtons there. So I have 3.5 times 10 to the negative fifth newtons minus 5.83 times 10 to the negative 6 newtons. And altogether then I get a total of 2.92 we can round to times 10 to the negative fifth newtons, and your direction would be upwards.